There we go.
We'll find out. We had just, any questions?
Yeah.
Yeah, I was in one of the practice tests, and one of the questions was like a circuit, and you're asking where to put the two
The leads?
leads for maximum resistance. I can't grasp my head around it, I don't know how it works. Yeah,
Was that on the 2020 test?
I think so, yeah, the most recent one.
Yep.
And there's like no numbers on it either, so I don't know, I just had a hard time figuring it out.
This was the configuration, if you needed it.
Just before I did the square.
Maybe so.
It is. All right, so. And the resistances are equal.
Yes.
So it's starting off well with each of the four resistors identical in resistance, and there's 5 resistors here. All right, so where I put the leads basically creates a junction. So if I put the leads there and there, well, actually, I start out with, I have a junction here, a junction here. Actually, all of that is a junction. All of that is a junction. I'm gonna include that, a junction here, a junction there.
Series, you just add them together, right, for resistors?
For series, yeah, just add them together. So if I put the lead somewhere, I'm creating new junctions. And where that makes a difference is series will not have a junction in between them. So if I put the lead here and here, those are junctions. This is no longer in series with that. And so there's a certain amount of trial and error here. All the resistances are the same. So you can either make up a resistance or just treat them all as R. I'm just gonna make them all 1 ohm. That's problem. If you're gonna make up a number, again, don't use 0. So they're in parallel. So so the leads are there and there. Those are in parallel because I have 2 junctions on each side. There's nothing in between the 2 junctions other than the resistor. Those are in parallel. They will have the same voltage, and the equivalent resistance is the reciprocals. So add the reciprocals, take the reciprocal of that, and if that's 1 and 1, the equivalent resistance is 0.5. These are in parallel. Actually, I have a junction there.
In series.
It splits, comes together. Those are still in parallel because that's not a new junction. Oh, that is a new junction. It's like that. So if I put the lead there,
Still looks parallel to me.
Yeah.
so that's the same as if I put it there. And
They'll still be in parallel.
the different, yeah, those are parallel. So that is 0.5. And that's in series with that, so that gives me 1. And so what I've reduced it down to is I have a lead, I have this resistor, and I have that resistor. So I end up with 0.5 as my equivalent resistance.
So in that configuration, you would most likely end up with the minimum equivalent resistance.
I'm not gonna make that judgment yet. If I put now, realize that putting the probe here or putting the probe here, there's no difference. In a circuit like this, we assume that the wires have no resistance. And so anything along here is the same thing. There's probe anywhere along there. Just like anything along here is the same. Anything along there is the same.
What if you did the bottom left corner and the top right?
So bottom left and top right, so like, bottom left, top right.
Yeah.
What I'm getting towards here is we basically have 3 different places I got this. That should take care of all the combinations. There might be another one I'm thinking of right now. But, so if I put it here and here, those are still in parallel. Those are still in parallel. This parallel structure is in series with that one. So I have a 0.5 up there and I have a 1.5 on this part. And so that 2/3 plus 8/3. So I think 3/8. That was just the equivalent resistance.
So the top part, you only have a 0.5?
That's 0.5 right there.
Yeah, what happens, okay, so it's traveling around, like from the bottom left or whatever. What happens when it gets that top junction before the top right?
The top junction before the top right
Yeah, the middle one.
gets to here.
Yeah.
Sorry, what happens to the current?
Yeah.
If the current's flowing this way, it would split. Not quite sure I'm understanding your question.
Well, and we're following the current on both sides of the leads, right, to figure out which resistances you have.
Okay. Alright, so, sorry, I cut you off.
Is that right?
Let me see if I'm picturing your question properly. I have a little bit of thinking. Alright, probes here and here. I'm going to assume current is flowing that way. So the current would flow in and flow this way and this way. You get to this junction and flow that way and that way. This is going to flow across there and across there, come back together again. This is going to join up, those will join up, and then we get the current.
No, it doesn't go back down when it gets to that middle junction, because of the other current on the other side or something?
It doesn't go back, oh, as in this would then spiral down?
No, so clockwise from the bottom left, after you go through the parallel ones, like you reach that middle junction there, why does it not go down?
Because the current wants to go this way. This is gonna be a high voltage and a low voltage, and the current, since I have current flowing that way, current wants to go this way.
Is it also because there's current flowing from the bottom up too? And it like locks it
Yeah,
or something?
and it could be wrong. I mean, it's, you know, if I have one in the wrong direction, it doesn't change equivalent resistance. So, since I'm not actually trying to find the current here, I suspect that this is what would happen. Because I know it has to flow in here, it has to flow out there, so this is gonna go that way. It's not like I'm gonna have current flowing away from the direction it wants to go. This is all one junction here, really.
Okay,
So anything that hits that junction would.
So I guess, yeah, if it goes down, it's flowing away from the direction it wants to go also then.
Yeah.
Okay.
Can you describe, I mean, when you say that junction, like, what exactly you mean by that?
All right, so what I'm claiming is that, again, let's have the leads there. So I have a lead here, and as it gets to this point right here, The next step is it's gonna go through one of these three resistors. Which means that I could write it like that. Then this one, the bottom one, could potentially go to one of two resistors. These would join up and get back to here, so then they would all sort of they would join up again. I mean, this is the same as that.
Doesn't have the same visual appeal, but sure.
But at least it makes it a little bit clearer what's parallel and what's series.
Yeah, the bottom
Those,
makes more sense.
those two are parallel to each other. So if that's 1, 2, 3, 4, and 5, that's 1, 2, 3, 4, and 5.
So I guess we could start out by redrawing the circuit if we wanted to.
And I've had some textbooks which have exercises where they want you to do that.
So is that a junction, like what?
So this is a junction here. That corresponds in the bigger drawing, or in the original drawing, as that.
So where it has like potential to go any different way, that's a junction?
Yes.
Where's the other one on there, at the end?
This junction right here would be this right here. And this junction right here is this up here. Where they all sort of, well, 3 doesn't flow directly into it, but 1, 2, 4, and 5 flow directly into it.
However, if you had another wire connected to it that doesn't go to a capacitor or resistor or anything, it's just like a wire that reconnects somewhere at the point where it connects to the other wire is not a junction, right? The new wire.
If you're talking about a wire that does that,
Yeah,
then no, that's not, because it's a dead end, current's not gonna go down a dead end.
or even if it goes down and then back up or something.
If it did that, then again, it doesn't do anything. Technically, they are junctions, the current would get to here, and if that is no resistance, and this is no resistance, then logically, half would go one way, half would go the other, and they meet up again.
Yeah, it doesn't electrically add anything, so.
Correct. Now, in reality, if I had a wire like that, and this is the scale, more current would flow through this than this, because that's a shorter wire, therefore less resistance. If I had a wire doing that, then that is a junction now. Current's gonna get to here, it's gonna go, most of it's gonna go the path of least resistance, and if that has no resistance, it's gonna bypass this and short circuit.
What do you mean short circuit, what?
You're bypassing a piece of equipment, or, you know, if that's a light bulb, the light bulb won't go on, because the current is bypassing. In essence, a short circuit is when two wires meet that weren't expected to meet, and current bypasses whatever goes down that path.
What's the difference between resistance and resistivity?
Resistivity is a property of the material itself. Resistance is,
And that's ohm meters, ohms times meters for the resistivity.
yeah,
And
and the
resistance,
symbol, that's resistivity, that's resistance.
yeah,
And the mathematical relationship, the resistivity, which is material dependent, times the geometry, times the factor dealing with the geometry of the wire itself. So you could say that resistance is dependent upon not only the material, but how the wire is made, whereas resistivity doesn't care about how the wire is made. It's the material that matters.
yeah, okay.
Can you do number 2 from the same test where it's talking about graphs of,
I like that question.
current versus time on the different setups of the circuits?
I haven't drawn out.
Fairs.
I'm pretty sure I get the first one, it's just like a straight line because the current is the same even after a resistor,
You can set
right?
up a matrix calculator.
Alright, so we
Solve
had
for
power supply and,
One with a resistor,
Mike messed that up.
Gives that out.
You can.
second one has just a
I
capacitor,
can just take a picture.
No, I don't need it.
third one has a capacitor and a resistor
Mm.
in series, and the last one has a capacitor and a resistor in parallel.
capacitor and resistor in series, so.
Yeah, that's right. And the last one is resistor and capacitor, it's, parallel.
And I think there's a switch, they all start at zero, so you
No,
turn on
there's
the power,
switch, but,
or you start out with, you turn on the power supply? That's a question too.
time begins at the moment the circuit is complete.
Okay.
It says all the graphs begin the origin too, I didn't really understand that.
And so it starts out with the circuit not completed, so there's no current running through it. So if I did a plot of current versus time,
Oh, wouldn't it
It
just be an
would be at
immediate
zero.
jump?
pardon?
It would be like an immediate jump then?
Yeah, but it starts at zero. You make the connection, and so it goes from zero to something not zero. So in the first one where I have just a resistor, it's gonna jump up to whatever the resistance is, so we have Ohm's law to tell us what the current would actually be if I know the voltage and the resistance. It's just gonna get up to it very quickly, and then flatten out.
And that's because resistors don't like stop the current, like the current's always the same even through
Yeah.
resistors.
Capacitor though, what a capacitor is gonna do is, it starts out with a lot of charge. I mean, charge flows very freely to start with, and then it gets harder and harder. So, the current should start out, I mean, there's practically no resistance here. So it starts out, jumps up very quickly. But then, as more charge builds up on the plate, it gets harder and harder to put a charge onto it. And so then it should start to, the current should go off to zero. Because when the capacitor is, once the capacitor is full, there's no more charge getting put on it, therefore there's no change of, there's dQ to T is zero.
And that relationship is, x cubed, not x cubed, 1/,
It's a exponential
yeah,
drop off,
so negative,
the e to the negative something.
okay.
We have an equation that has e to the negative something. I don't remember what it is for, but like e to the negative 1/t over something.
There, E shows up in a lot of equations.
Oh, yeah, it's the
Filling in
max,
faster.
1 minus e to the negative t over time constant.
That's the charging of the capacitor, and then I guess if you got rid of that one minus, then it's the discharge of the capacitor. All right, if I throw a resistor in here, then, actually, that should actually be steeper than what I had right there,
Why?
because I have no resistance to start with.
I thought resistance doesn't matter for current.
Well, resistance is going to something, if I took a battery, have a wire, and I just connect them, then you've got, if this is an ideal wire, I have no resistance, charge would immediately flow and the battery would be dead. As it is, it's very quick. I mean, had a battery fall over a truck and discharge on the side of the truck. Because whoever changed the battery did not do it properly. So in this case right here, when I've got nothing on the plate, there's no resistance, so it should be almost immediately, it should more quickly than this does with the resistor in it. So this, once it gets up to full power, or the full current, it's gonna be flat. It's just a matter of how quickly it gets there. And so I'm going with resistance, it will,
Okay, but in your first graph, the current, or the resistor isn't affecting the current, it's just just getting up to a current, and the current is staying the same as it moves around the circuit.
Once we get up to that current.
So it does affect, current until it gets up to its maximum amount or something?
Yes, yes,
Oh, that I did not know.
okay. It's quick, I mean, we're talking microseconds.
I mean, is it something that you would mark off for on a test if we didn't show the difference in slopes of how fast it got to?
It would be a minor deduction if it is one. Realistically, if the first one I see doesn't the nice way, I'm gonna go, oh, okay, good. And then everything goes, if I grade 3 of them or 4 of them and no one gets it, then I'm probably gonna go.
Well, yeah, because if you're talking microseconds, I mean, you're like talking like different, you drew it somehow, like, I don't know.
It's a neat subtle. More importantly is when we get down to some of the later ones where it will make more of a difference.
Speaking of. Third one.
Right, so the third one, you make the circuit, it's gonna, again, start at 0. I know that it's gonna quickly get up to some value, but with a resistor in there, well, it's gonna start out with something like that, but as charge builds up on the capacitor, it's going to start to slow down the current. And so I'm gonna get a rise, and then the current should start dropping off as the capacitor starts to fill up. And so, since the current is not gonna be as great here as here, or maximum current is not as great here as here, because I do have extra resistance, then it will fill up less slowly. I have less current traveling per unit time.
So are we measuring these like after it completes the circuit once? Basically, is that where the graph starts or something? That's like where?
At the moment when I set the switch, I mean, it's gonna go from 0 to something, and so I'm trying to capture that transition.
They didn't have the switch on the test, so what would you know when to start?
But I set it started at the origin.
Yeah, no, that's fine, there's no switch, but, I'm wondering why the third one now looks like the top one, then if you have a capacitor first and then a resistor.
It should not